Hello everyone, my name is Camilo Escobar Velázquez. I work with the Software Design Lab from Universidad de los Andes in Colombia, and today I'm going to present IDRATE, a tool for automated detection of internationalization issues in Android apps. First, we define internationalization as the set of efforts required to enable the usage of an application in different languages. As it can be seen in the bottom left image, this is not related only to the translation of text, but also to the validation of the design metaphor in the final languages. Why is internationalization important? Because mobile markets provide access to apps around the world, and being Android one of the top operating systems for mobile devices, enabling the usage of an app in different countries and in different languages might help track attention and more users. Now, how is internationalization enabled in Android apps? For that, Android apps use a set of files called strings.xml. For each language, there is a specific folder named after its acronym storing the aforementioned file. For example, for English, there is an EN folder, and for Spanish, there is an ES folder. Nevertheless, the default internationalization protocol defined to generate a new version of the strings.xml file requires the manual translation of strings. And as you might notice, this is an error-prone and cumbersome process. What has been then proposed to tackle this? There are previous work on the detection of need to translate strings in web apps, and also in the translation of strings, but in an offline mode. Also, there is previous work on the detection, localization, and repairing of internationalization presentation failures in web apps. Therefore, to summarize, we have seen that IDEs do not have automatic translation of strings. The detection of translation of need to translate strings is performed offline. Also, that previous work has tackled internationalization, but for web apps. And we also know that automated detection of internationalization issues in Android apps should consider the specifics of Android programming model. Therefore, we created IDRATE, that is a tool for the detection and localization of internationalization failures for Android apps. IDRATE is publicly available in GitHub, and you can find an online appendix with more detailed information following this QR code. IDRATE has four main capabilities. That is the detection of hard-coded strings. Second, the detection of non-internationalized strings. Third, the automated translation of strings. And fourth, the systematic exploration of translated apps, along with automated detection of changes due to internationalized strings. In order to achieve this, IDRATE is based on four main strategies. First, the static analysis at APK level. Second, automated translation of strings. Third, dynamic analysis of Android apps. And fourth, the usage of layout graph as base graphic user interface model. Following the last idea, the layout graph is a graphic user interface model that depicts the relations between all graphic user interface elements. It was proposed by Alamir and Halfon in their paper, An Empirical Study of Internationalization Failures in the Web. Before understanding the inners of IDRATE, we first need to see what are the parameters and process required to execute it. IDRATE is a Maven project, and it requires 7 parameters for its execution. First, the APK file path. Second, the APK package name. Third, the path to external libraries folder, where the systematic exploration explorer is stored, and new libraries can be located in case you want to extend it. Fourth, the language configuration file path. Fifth, the amount of strings within the app that are untranslatable, for example, the app name. Sixth, the folder where results must be stored. And 7, the emulator or device ID that is going to be used for the test. Finally, the language configuration file that I mentioned before is a properties file that depicts the languages that must be used for the test. Now that we know what we need to execute IDRATE, we propose the following workflow divided in 4 main stages. The first one is the preprocessing of an APK under analysis by first using the APK tool library to unpackage and decode the APK into an intermediate representation called Smiley. The second step is the hard-coded strings detection, that is performed by using static analysis of the processed APK, generating an AST model that enables the localization of hard-coded strings within the Smalley representation. The third step is the non-internationalized strings detection made by the identification of string resources that are not defined in a specific language when compared to the complete set of strings defined on the default language. The second stage, called translation, is in charge of using the translation service to process and translate the non-internationalized strings and generating the associated strings.xml files. For our current version, we use IBM Watson Translation Service. Now, once all the non-internationalized strings are translated, Hydroid generates a new APK that contains all the strings XML files for the selected languages. The third stage is in charge of the dynamic exploration of the internationalized APK to identify the impact generated over the graphic user interface. Therefore, in order to do this, Hydroid uses an approach based on the systematic exploration of the Android app. Since our main goal is to be able to compare the different versions of the apps, we explore the app on a device with the language configured as the default language, extracting the visual properties of the visited stage to build first the layout graph, and second, a reproducible log that could be used later. Based on the generated log, we re-explore the app using in each one of the steps one of the selected languages. As a result of this stage, Hydroid generates a set of layout graphs representing the different languages version of the app. Finally, the last stage is the detection of internationalization collateral changes by exploring and comparing the layout graph of the default language against each one of the languages. Therefore, since the layout graph depicts the relation between elements of graphic user interface, if in any of the used languages a collateral change happens, by comparing the layouts graph, we are able to recognize it. Finally, the process finishes by the generation of a report. Now we have seen how to run Hydroid and what happens when we execute. What are we missing is to understand the final result automatically generated. So what is inside the final report of Hydroid? First, we have the hard-coded strings report that presents the identified strings in three-level layout, starting with the class name, followed by the method name, and finally the value of the hard-coded string. Second, a file depicting the IDs of the string resources that were missing from the used languages according to the default language. Third, the report of internationalization collateral changes containing for each case the explorer state ID, the ID of the graphic user interface element, and a list of IDs of elements that went through a relation change due to internationalization. But does it really works? We performed an empirical study on internationalization collateral changes and bugs on Android apps. We executed Hydroid on 31 open source Android apps and identified automatically 402 internationalization collateral changes. We analyzed manually the identified collateral changes and generated a taxonomy of the changes and bugs found on Android apps. Concerning Hydroid capabilities, future work will be dedicated to: first, translation of hard-coded strings; second, enhance of the final report; and third, to extend the validation of results in terms of precision and recall. Thank you for your time, and we hope to hear your questions on the QA session.